Hey, discrete math students. Welcome to this Going Deeper video on the definition of mathematical proof. I feel like you're in a position now where we can consider a definition of mathematical proof, and you really be able to comprehend it. It'll make a lot of sense. And the reason why you're in that position now is because we have lately considered the definition of logic proof and been thinking about logic proofs. Logic proofs, knowing logic proofs, I think is a huge advantage when you're constructing mathematical proofs because it really provides the pattern for how mathematical proofs are done as well. And even though mathematical proofs look kind of different, many of those same principles carry over so nicely, and it just helps it makes a lot of sense why we do a lot of the things that we do in mathematical proofs. So let's just recall a few of the highlights from our study of logic proofs. A proof, of course, logic proof in this context, is an argument of an argument with premises A1 through N and conclusion C, is a finite list of formulas. The last formula is C. And each formula on the list is either a premise from the argument or a logical consequence of previous formulas in the proof. Okay, and so we did that. We saw that, if you can construct a proof, then that shows that the argument is valid because you can get to the conclusion using the assumption that the premises are true. Okay, we labeled the steps of our arguments SI. And one key thing that we saw is that each step in a logic proof must be justified. There must be a reason why you can put that step in. And for logic proofs, it's a fairly straightforward situation, abstract situation. There are only three ways in which a step could be justified. We looked at those three, and we've employed all three of them in doing various logic proofs. Okay, so again, when we go to mathematical proofs, we're going to see that there are more possible reasons types of reasons that you can use to justify a step in a mathematical proof, but the spirit of it is very much the same. Math proofs also have steps. Each step has to be justified. In the end, you want to reach the conclusion. Okay, so now let's give our definition of mathematical proof. So you've got some statement that you are trying to prove, and we will call that statement C. That was the conclusion before in our argument, and that's, of course, not a coincidence. A mathematical proof is also a sequence of statements. We usually don't label them like this, A1 through AN, but we could still think of them that way. These are called the steps of the proof, and each step is either, so it's got to be one of the following 5 types of things. It's either a permissible assumption, such as an axiom, or we have other, facts that we're assuming as background knowledge. Those kinds of things are permissible assumptions, and there's an understanding that they are okay to use. Okay. Another type of step can be a step that is legitimized by applying a certain proof method. Just as one example of that, we can make the hypothesis when we are proving a conditional implication. The direct proof method tells us that that is okay to just assume that the antecedent of that conditional is true. Without that proof method, you'd be like, well, why could you do that? But direct proof tells us it is okay. Result of applying a definition. So again, we don't just state definitions in proofs, but we may have a step in our proof and we say, okay, I'm going to apply a definition I know to what I had in this previous step. That is fine. It can help you get further along in your proof. We have known or previously proved propositions. Once we have proved something, we don't have to reinvent the wheel every time. We can use that previous result in future proofs. Okay, and just again, the presumption there is that, hey, you already proved it. It's known. It is now a piece that you can use in building other proofs. like a pre-assembled component. And then fifth, this one looks awfully familiar from our study of logic proofs and from our definition. It's a logical consequence of some previous step or steps in the proof. You can get things like that from logical equivalences and rules of inference. So steps 1 through 4, really all 4 of those steps are in that role from logic proofs of just premises of the argument. And so what we see in a mathematical proof is that typically we're working with a much broader palette of premises that we have at our disposal, as opposed to the sort of very strict constraints of a logic proof where those premises all have to be listed out in the argument. We have a lot of background material that we are able to work with, and again, the context will dictate exactly how much you can presume from the broader world of mathematics. But essentially, anytime you have an axiom or a previous result or a definition that you're applying, all of those things are more or less incorporated into the bank of premises that you can work with in deducing your statement that you try to prove. One thing, so again, mathematical proofs are different in their format than logic proofs. Logic proof, we have kind of this 2-column, list of steps and reasons. Mathematical proofs are written in natural language typically, and in particular, they are written in paragraph form, not that 2-column form or line by line, with a separate step on each line. That's not typically how it's done. But again, the underlying spirit of the structure is the same, even though the format looks a bit different. So I'll put here as an important point of emphasis that math proofs are written in paragraph form, because that's typical for natural language, right? We write in paragraphs. So that's one of the big differences. But it's just kind of a superficial difference, I guess you might say. Written in paragraph form. There we go. Okay. So let's look at some upshots of this definition of mathematical proof. Okay. You'll notice that when we're writing proofs, hopefully you've noticed as I've been doing it, and perhaps you've noticed some comments that I've put on yours as well. You want to have a strong conclusion to a proof, an explicit conclusion that says, hey, we really have proved what we were trying to prove. And that, again, is a direct parallel of something in the world of logic proofs where you know that the last step in a logic proof is always the conclusion of the argument that you're trying to show is valid. And so similarly in the setting of a mathematical proof, it makes a lot of sense and it helps with the communication and the clarity if when you get to the end of the proof, the last thing that is there is something like, therefore we have proved this, where this is the original statement. Okay, and again, that's required in a logic proof, but most of the time that is done in mathematical proofs as well. I will say that there are certain situations where it's not done quite that explicitly. There are very common situations where you don't put that last step because it'll just be so obvious to everyone who knows this proof method that once you've done this and this, the conclusion is obviously going to follow. I don't know if I would say that that's a great practice, but it is one that in certain situations is commonly done, such as with the choose method. You choose your arbitrary element, and then you work through and you say, therefore, for this arbitrary element, the statement is true, or the property is true. Okay, now really maybe we should go back in there and say, therefore, for all elements of that domain, the property is true, but typically that's not done. So there's one example of that. But as a general rule of thumb, it is good to put that conclusion explicitly in there in the last step of the proof. And again, we get that from logic proofs. And it's in our definition of mathematical proof as well. One key principle, again, carried over from what we did with logic proofs, is that every step in a proof must be justified. You don't have a separate column, where you list your reasons, but they should be worked into that paragraph form, and don't be too quick to presume, oh, this is obvious, I don't need to give a reason for it. Typically, we want to give some sort of justification for each step we put into a proof is legitimate, some type of reason, even if a brief one, or just a reference to something that we've done before. Now, thinking about those 5 reasons that we can use to justify a step in a mathematical proof, one of them holds special significance. And that is because as you proceed to proving more complex statements mathematically, if you had to go back to like definitions and axioms every single time, your proofs would, grow sort of longer and longer and become more and more complex, and it would become hard to even follow what's going on. So a great blessing here that we have is this ability to use things that we've already proved in future proofs. And a lot of times we can, again, not reinvent the wheel, but really kind of save ourselves some time by using some pre-assembled components in constructing our proofs. Okay, so once we have proved one thing, we can then use that in other proofs as a step. Okay, a great illustration of this is with parity results in number theory. So parity results are just some basic, you might say, facts about even and odd numbers and how they behave under the arithmetic operations in number theory. You have already actually proved a number of parity results. We just haven't framed them as such. And once you prove them, you can use them in proofs. So in this case, it'll be a matter of, have you watched this video? And then if so, then you'll know that, hey, these are okay to use in the future. Okay, so let's look at some of these parity results. I wouldn't say all of them, but the basic ones, let's say. Okay, first of all, definition of parity. This just has to do with evenness and oddness, but we do it by comparing 2 integers, right? It's not just like a single integer that we would usually say, oh, that has parity. You could say that, but usually we're comparing. So to say that integers x and y are of the same parity means that x and y are both even or both odd. So you can see in that definition, there's disjunction, as well as conjunction, so it's definitely some logical structure there. And then similarly, say x and y are of opposite parity means that either x is even and y is odd, or y is even and x is odd. There too, conjunction and disjunction, just with a little bit different arrangement. Okay, so a lot of the parity results we can actually frame in terms of this idea of same parity or opposite parity. Let's see some examples. Okay, the sum of any 2 integers of the same parity is even. I think that you have proved this, altogether. I think you've proved it. You've proved it perhaps just in pieces, because when we say that 2 integers have the same parity, there are really 2 cases there. They're both even, or on the other hand, they're both odd. And I think you proved that if 2 integers are both odd, then their sum is even. And if 2 integers are both even, then their sum is even. So put together, you have proved this. And it's similar in many other cases. The sum of any 2 integers of opposite parity is odd. Again, perhaps in different words. I think you've proved that in some check your understanding problems. The product of any integer and any even integer is, if you want to pause, you could do that. See if you can fill in that blank. But in fact, it fills in with even, right? Product of an even and anything else is even. Again, fairly easy to prove if you have not already, which I think you may have. And, that's all I had on my list. But of course, there's more, right? Again, there's several ways you can kind of run with the ones we've got so far and generate other ones. And of course, there's some that are maybe not quite so basic as well that are still interesting too. But if you want to pause and try to think of some, feel free. Okay, welcome back. Let's see. Did I put anything else under here? No. Okay, so I can just go like 4. Okay, the product of any integer and any even integer we did already. The other case would be the product of 2 odd integers. The product of 2 odd integers is odd. That's a parity result. You proved that somewhere. I don't know if it was on an exam or maybe on problem assignment. Somewhere you proved that. What else could we do here? We got addition, we got multiplication, we could do subtraction. So for 5, at the risk of being a little too brief here, we could make 5 like a duplicate of number 1 and just say that the difference of any 2 integers of the same parity is even. And of course that you could either do as a corollary of parity result number 1 up there, or you could prove it much along the same lines as parity result 1 is proved. And then naturally 6, you could also do difference instead of sum. In number 2, getting a lot of lines crossing here. We'll go around this way. Okay, so you could do them with differences. Division? No. This is number theory. We can't do division. But you can probably think of others as well. There's some interesting ones besides these, but I think these are the basic ones because they concern what happens when you combine 2 integers with our 3 arithmetic operations. I think we've got all the cases covered for that. So yeah, these are parity results. Whether you've proved all 6 of them, maybe not, but I think you've proved enough of them that we can take them as background knowledge from now on. So what will a proof like that look like? Some of you have already tried to write proofs like this before we said that these are fair game, which we're doing now. Okay, so again, now, once you've proved these, which let's say that we have, in proving conditional implications involving parity, you'll have 2 possible avenues in which to so 2 possible kind of, not methods, but 2 possible approaches in proving another result about evens and odds. You can go back to the definitions like we've been using so far. You can always fall back on those. But now you also have the option to use parity results. And of course, some people try to mix those together. It's usually kind of a mess when you do that. It's best to stick with one approach or the other. Okay? And also, when you're proving the parity results, to whatever extent you have not proved them yet, or if you need to prove them again, you can't generally use parity results to prove the parity results. You get pulling yourself up by your own bootstraps type of vibe from that, or circular reasoning. So we really need to use the definitions to prove the parity results, and then we can build from there. Okay, so for instance, let's take a look at one simple example. If n is an odd integer, then 3n plus 7 is an even integer. Okay, so this is a conditional implication. I'm going to use direct proof on it. But this time, rather than going back to the definitions of even and odd for this, I'm going to use parity results. Okay, assume, first of all, it's direct proof, so I need to make my hypothesis. So I assume n is an odd integer. Okay, not going to go back to the definitions, as tempting as it is. I always like the definitions myself, but I'm going to do something like the following. I'm going to say, by a known parity result, that the product of 2 odd integers is odd. Okay, I'm going to say that, hey, 3n is odd. And just for a little more evidence in there in terms of putting this all together, I'll say since 3 and n are both odd. Okay, and let's take it as a permissible assumption here that 3 is odd. and n, of course, by our hypothesis is odd. So now we've got that 3n is odd. Okay, now we want to look at 3n plus 7. Well, 3n is odd. 7, again, we can take for granted that 7 is odd. When we add those together, we're adding two integers of opposite parity. And so one of our parity results tells us that that result is going to be even. Okay, so I'm going to say as a sum of two integers of the same parity, I was going to put in here, just to make it extra explicit, the same parity. What parity are they? They are both odd. Okay, now I'm going to say 3n plus 7 is even by another parity result. Okay, and again, we want to end our proofs with what we were trying to prove as our conclusion. There it is. 3n plus 7 is even. Got it there in my last sentence. That's my conclusion. Nice and explicit. Getting to that, relatively short and sweet, since we build on previous results. Now, in this case, you can compare what we did with an approach using the definition. Probably won't be a whole lot different here. But again, as you go to more and more complex statements that you're trying to prove, more and more you're going to see, oh yeah, there's definitely some value here in using those previous results, utilizing what we know rather than going back to the definitions every time. So I hope that this has been clarifying and empowering in terms of maybe some of the aspects of why we do proofs the way that we do, or why we write them as we do. It's kind of going back to that culture of logic proofs and transferring some of the principles there into the world of mathematical proofs. All right. See you next time.